All right, welcome to another deep dive. This time, we're going where the lab bench meets the computer screen.
Sounds pretty high-tech.
It is. We're talking about computational catalysis.
Yeah.
It's like having a superpower.
Yeah, a superpower. Okay, I'm intrigued.
Using simulations to design and optimize catalysts. Those amazing molecular machines.
Right. Catalysts, yeah. Essential for so many reactions.
And you, dear listener, you're already deep in the world of chemistry and material science, so you know just how crucial they are. But think about understanding them at the atomic level.
Oh, wow. Getting right down into the nitty-gritty.
That's what we're unlocking today.
Unlocking, I like that. And it's not just about understanding, is it? It's about using that knowledge, to predict how a material will behave.
Exactly.
What kind of reactions it'll speed up, and even, designing entirely new catalysts.
100%.
That's the real game changer.
Now, you sent over a presentation. Looks like it's from a graduate-level course on this topic.
Yeah.
It's got a ton of information on different simulation methods.
Lots to cover.
But there's a big emphasis on DFT, density functional theory.
DFT. Definitely the workhorse in this field.
So like the star of the show.
You could say that. It's like imagine having a powerful lens.
Okay, a lens, go on.
That lets us zoom in real close and see how electrons are behaving inside a material.
Oh, wow.
And that's crucial, really crucial, because electron behavior, well, that's the heart of chemical bonding reactivity.
Yeah.
The essence of catalysis, you could say.
Okay, I'm already intrigued. And speaking of intrigue, the presentation starts off by asking this question. Why are simulations so crucial in catalyst research?
Ah, yes, the classic question.
So why bother with all this, computation when you can just, run experiments in the lab?
You'd be surprised how often that question comes up. But think of it this way.
All right, I'm listening.
Experiments give you the what. What products are formed, how fast the reaction goes.
The observables.
Right. But simulations. Simulations give you the why. Why does this catalyst work better than that one, They let you peek into the mechanism, understand those subtle interactions at the atomic scale that drive the whole process.
So it's like having X-ray vision for your catalysts.
Exactly. You're seeing what's happening beneath the surface.
I love that. But what about the different simulation methods? The presentation mentioned quite a few. There's quantum mechanical, atomistic, mesoscale, continuum. It's a bit overwhelming, honestly.
It can seem that way, sure, but think of it like zooming in and out on a map.
Okay, a map analogy, I can work with that.
Each method lets you look at a different scale of the whole catalytic process. Quantum mechanics, like DFT, that's like looking at the street level.
Okay, street level, got it.
Seeing the individual atoms and electrons. Atomistic simulations, they zoom out a bit, focusing on groups of atoms, molecules.
So like a neighborhood on the map.
Exactly. And then mesoscale, that's like looking at, whole neighborhoods. And continuum is the big picture, like the whole city.
Okay. I'm starting to get the picture.
Good.
So if you want to understand how a catalyst binds to a molecule, you zoom in real close with DFT.
Yeah.
But if you want to see how that catalyst behaves in a complex reaction environment, you might need to zoom out to a different method.
Exactly. You're catching on quick. And the real magic happens when you can combine these different methods.
Combining them. Interesting.
It's what we call multi-scale modeling. Powerful stuff. It's like imagine a set of maps, all at different scales. So you get a truly, truly comprehensive understanding of what's happening.
Multi-scale modeling. That
Yeah.
sounds incredibly powerful. But for now, let's focus on DFT. Since it's, such a big part of this presentation, it seems like there's a whole world of DFT software packages out there.
Oh, there are.
VSP, Quantum Espresso, CASTEP.
Yeah, those are the tools of the trade. Each one has its strengths, its nuances, but they're all based on really the same fundamental principles of DFT. They let researchers calculate all sorts of things, like charge density, for example.
Charge density. What's that tell us?
Tells you how electrons are, distributed around the catalyst. Or the work function.
Work function, huh?
Yeah.
Another one of those important properties.
Oh, yeah. It tells you how much energy it takes to rip an electron away from the surface. Important stuff.
Okay, starting to see how DFT can provide a wealth of information about a catalyst. But how do we actually use that information to predict how well it will perform? The presentation mentioned something called descriptors. What are those all about?
Descriptors. Think of them like fingerprints, of a catalyst. Measurable, properties that we can calculate using DFT, and they give us these clues about how a catalyst will behave in a reaction. Things like absorption energy,
Absorption energy.
how strongly the catalyst binds to reactants, or the D-band center, which tells us about the catalyst's electronic structure and, its ability to donate or accept electrons.
So it's like having a cheat sheet that tells you a catalyst's strengths and weaknesses.
You could say that. And one of the probably the most fundamental concept we use to understand catalyst performance, it's called the Sabatier principle.
The Sabatier principle.
Yeah.
Okay, never heard of that one.
You might have heard it called, the Goldilocks principle of catalysis. Basically, it says that a good catalyst binds reactants just strongly enough. Not too weak, not too strong, just right.
The Goldilocks principle. I like that.
And descriptors. They help us find that sweet spot.
Okay, I see how this is all coming together now. You use DFT to calculate these descriptors, and they give you insights into a catalyst's behavior, and then you can use those insights to predict how well it will actually perform. Pretty amazing, right?
It is, and it gets even better. The presentation actually walks through a really cool example, modeling a gold-palladium catalyst. It's like taking all the theory we've been discussing and putting it to the test in a virtual lab.
Oh, that sounds perfect. I'm ready to see how all these DFT calculations and descriptors translate into real-world catalyst design. What are the key steps in this modeling process?
Well, the first step is building a model of your catalyst. Like, you're essentially creating a digital blueprint, right?
A blueprint.
Defining the positions of all those atoms in the catalyst structure.
So for like a gold-palladium catalyst.
Yeah. For a gold-palladium catalyst, you'd need to specify, the arrangement of the gold and palladium atoms based on, of course, experimental data. You need to know about the catalyst's composition and structure.
So it's like, I don't know, building with Legos, atom by atom.
But on a
Maybe
computer.
Like digital Legos. Got it.
Exactly. Once you have that digital model, then you unleash the power of DFT.
Unleash the power. Okay.
You run a bunch of calculations, a series of them, to get information about the catalyst's electronic structure.
Electronic structure. Right. Things like
charge density, work function, density of states, all that good stuff.
So you're like running a virtual experiment on this digital catalyst.
That's a great way to put it.
Probing its inner workings, but without ever, actually having to set foot in a lab.
Exactly. And the really cool thing is you can tweak the model, change the composition, introduce reactants, and see how it all affects the results. It's pretty powerful.
So you can explore, a ton of different possibilities.
Oh, yeah. All within, the safe confines of your computer.
That's pretty incredible.
Yeah.
But it's not all just playing around in a virtual sandbox.
Of course not.
At some point, you need to connect these simulations back to, reality.
100%. That's where the real power comes in, comparing the simulation results to experimental data.
Right. The lab results.
Yeah. This helps us validate our models, make sure we're on the right track, refine our understanding of the catalytic process.
It's like this constant back and forth, right, between the computer and the lab bench.
Exactly. A conversation.
Pushing our understanding forward. So in this specific example with the gold-palladium catalyst, what kind of insights did the researchers get from the DFT modeling?
Well, they were interested in understanding, how the concentration of palladium affected the catalyst's activity.
For a particular reaction.
For a particular reaction, yeah. Converting NO to NH3. And what they found, using those DFT calculations, they found that even adding a small amount of palladium to the gold really enhanced the catalyst's performance.
So they were able to predict that just from the simulations?
Yeah.
That's pretty remarkable.
It really is. It really highlights, the predictive power of computational catalysis. And this is just one example. DFT is being used to study all sorts of catalytic processes, from simple reactions on metal surfaces to really complex reactions, ones involving enzymes.
So it's not just limited to designing new catalysts.
No.
It can help us really understand how existing catalysts work at, a fundamental level.
Exactly. Like having a microscope, but one that lets you see the electrons dancing during a chemical reaction.
All this sounds incredibly exciting. But I have to admit, it can be a bit overwhelming for someone, just starting out in this field. What advice would you give to a grad student who's, eager to dive into the world of computational catalysis?
First of all, don't be intimidated.
Right. Easier said than done sometimes.
It can seem complicated, but there are a lot of, there are resources available to help you learn. Textbooks, tutorials, workshops.
Specific recommendations for, our listener?
Of course. There's a great book, Density Functional Theory, a practical introduction by, I think it's David Scholl and Janice Steckel. Really solid intro to the theory and applications.
Okay, noted. And for online resources, anything come to mind?
Oh, yeah. The Materials Project website, absolute goldmine. It's like this treasure trove of DFT calculations, analysis tools, all sorts of stuff.
Fantastic. Any other tips?
I would say get hands-on experience with the software, as soon as you can. There are several open source packages available, like Quantum Espresso, GPaw, that are great for, getting started.
Get your hands dirty, yeah.
Exactly. And don't be afraid to, reach out to people. There's a really great community of computational catalysis researchers out there, people who are always happy to help.
That's really encouraging to hear. So it's all about diving in, getting your hands dirty with the software, connecting with the community.
100%. And don't forget, embrace the learning curve. Computational catalysis is constantly evolving, which means there's always something new to learn. It's what makes it so exciting.
This has been an awesome deep dive so far, covered a lot of ground, from DFT basics to real-world applications. But before we, wrap up, I have a feeling there's more to this story. Are there any limitations to DFT, things we should be aware of?
You're right. There's always more to the story. DFT is powerful, definitely, but it's not perfect. Like any computational method, it has its limitations. You're right. DFT is powerful, but not a magic bullet. Like any computational method, it's got its limits.
Okay, so even the superstar of computational catalysis isn't perfect.
Yeah.
So what are some of the things we need to watch out for? What are its weaknesses?
Well, I think one of the key things to remember is that, DFT is based on approximations.
Approximations.
It uses, simplified mathematical models to describe those complex interactions between electrons.
Okay, so if the results are based on approximations, how much can we trust them? How do we know if we're, getting the right answer?
That's the question, isn't it? The question every computational chemist grapples with. The accuracy of DFT, well, it depends on a lot of things. The type of system you're studying, the specific mathematical, what we call expressions you use, even the computational power you have available.
So it's not just a plug-and-play kind of thing.
Yep, not really.
There's a real art to, choosing the right settings and actually, interpreting those results, huh?
You got it. There's a whole field of research dedicated to developing and refining these mathematical expressions, what we call exchange correlation functionals. Choosing the right functional, that's crucial for getting accurate results.
It sounds like, I don't know, DFT is kind of like a high-performance race car. Incredibly powerful, but you need a skilled driver to really get the best performance out of it. Are there any specific situations where DFT might not be, the best tool for the job?
There are definitely some cases where DFT can struggle. Like, for example, it can have difficulty accurately describing certain types of chemical bonds, like van der Waals interactions, for instance.
Van der Waals interactions, okay.
Which are, these weak forces that can play a pretty big role in, in some catalytic systems.
So what happens when DFT hits its limits? Are there other computational methods that can, step in and fill the gaps?
Oh, yeah, absolutely. There's a whole toolbox of computational methods out there, each one with its strengths and, of course, its weaknesses. Some methods, like Hartree-Fock theory and post-Hartree-Fock methods, they can be even more accurate than DFT.
Right, more accurate. Okay.
But they require a lot more computational power, so.
So it's a trade-off then. Higher accuracy often comes at a higher computational cost.
Exactly. And for really big systems, really large systems, like proteins or complex materials, we might need to use methods that are less computationally demanding. Even if they're not quite as accurate, it's all about choosing the right tool for the job.
Okay, I'm starting to get a sense of all the complexities involved here. DFT is clearly a powerful tool, but it's important to be aware of its limitations and know when to reach for other methods. But what about the future? Where's this field headed?
Ooh, the future of computational catalysis. That's exciting stuff. We're seeing really big advances in areas like multiscale modeling, for example, where we're combining different methods to simulate catalytic processes across multiple length and time scales. It's really cool. And machine learning is playing a bigger role too, helping us develop more accurate and more efficient models.
It sounds like computational catalysis is like constantly evolving, pushing the boundaries of what's possible.
It definitely is. And for anyone who's interested in this field, whether you're a grad student just starting out or a seasoned researcher, it's a really exciting time to be involved.
This deep dive has been an incredible journey. We've explored the power of DFT, its limitations, and the really exciting future of computational catalysis. What a fantastic way to wrap up this episode.
It's been a pleasure sharing this journey with you.
And to our listener, we hope this deep dive has, you know, sparked your curiosity and inspired you to explore the really amazing world of computational catalysis. Keep asking questions, keep pushing the boundaries. The future of catalysis, well, it's in your hands.